All right, let's get right into it. Today, we're going to look at renewable energy a little differently, not just as a collection of sources, but as a whole system that needs to be managed. We're talking about a complete strategic framework, both from an engineering and an economic standpoint. So, let's dig into what that actually looks like on the ground.
So here's our game plan. We'll kick things off with the why, the strategic imperative. Then we'll get into the key integration tech. After that, we'll talk about optimizing the whole system, tackle some of the big integration challenges, and finally, look at the frameworks that make all this possible.
Okay, section 1, the strategic imperative. So why are we framing it this way? Why think of it as this big managed system? Well, it really comes down to 3 big drivers, things that everyone in this field is wrestling with day in and day out.
First up, and this is really the baseline for everything else, is enhancing environmental quality. We're not just talking about a nice-to-have goal here. For us, mitigating emissions is a core design constraint. It dictates pretty much every single technical and economic choice we make down the line.
And then, of course, there's the one that gets the budgets approved, economic competitiveness. This is where we move past just mandates and into hard numbers. We're talking about seriously cutting operational costs, protecting ourselves from those wild swings in fuel prices, and, reducing our dependency on volatile imports.
And that economic piece flows right into our third driver, ensuring energy security. Look, diversifying our energy portfolio, it's not just about having different types of fuel. It's a strategic move. It's about hedging against global risks and supply chain nightmares. It's about building resilience directly into the DNA of our grid.
All right, section 2, P integration technologies. So we've got our goals. Now, what are the actual tools we're using to get there? And let's be clear, we're not going to waste time on Solar 101 or Wind 101. You all know that stuff. The real action, the real engineering challenge is in the integration technologies.
Okay, so take a look at these 3. They're really the workhorses. You've got distributed generation, or DG, which is all about boosting reliability by putting power production right where it's needed. Then there's combined heat and power, CHP, which is just a super smart way to squeeze every last drop of efficiency out of your fuel. And finally, the big one, energy storage. This is the key to taming the intermittency beast. But here's the thing, it's not about any one of these in isolation. The magic happens when they're all working together, interlocking to create a truly resilient system.
Which brings us to section 3, optimizing the energy system. So how do we actually build this thing? This is where the rubber really meets the road for us engineers. It's a very deliberate, methodical process, so let's walk through it step by step.
Look, this isn't guesswork. It's a disciplined, repeatable playbook. Step 1, you start with a deep dive audit. You got to find those energy management opportunities, the EMOs. You know the saying, you can't manage what you don't measure. Then, step 2, you run the numbers. A really rigorous life cycle costing analysis to make sure it's all financially sound. Only after that, in step 3, do you actually get into the system design, integrating your renewables with solid controls like a BAS. And really important, this isn't a one-and-done deal. Step 4 is all about continuous optimization through things like preventive maintenance. It's a living system.
And I really want to double-click on life cycle costing for a second, because as we all know, LCC is the language of business. This is how we get these big, capital-intensive projects approved. It forces the conversation away from just the sticker price and focuses on the total cost of ownership, weighing that against all the savings over the entire life of the system. Let's be honest. Without a bulletproof LCC analysis, some of the best engineered projects are dead on arrival.
So, what makes it all work together? It's the control systems. Think of this as the central nervous system for the whole operation. Honestly, without these, all that expensive hardware is just a pile of dumb assets. You've got your building automation systems managing things at the facility level, your energy information systems giving you that crucial high-level data, and when you layer in smart grid tech, that's when you get the real-time control you need to make the whole grid responsive and intelligent.
Okay, let's move on to section 4, addressing integration challenges. Now, obviously, this isn't all easy. There are definitely hurdles, but the way we need to think about them isn't as roadblocks. They're engineering problems. And engineering problems have engineering solutions.
And the big barriers are probably no surprise to any of you. You've got intermittency, that's a physics problem. You've got the high initial investment costs, that's a finance problem. You have the strain on our existing distribution networks, which frankly weren't built for this. And then there's the people problem, a shortage of skilled labor. Each one of these needs a very specific solution.
And the good news is we have the tools. You're dealing with intermittency, the answer is energy storage and smart grid controls. Worried about the high upfront capital? That's where solid lifecycle costing and smart incentives come in.
Is the grid feeling the strain? That's a perfect case for distributed generation and targeted upgrades. See, it's not about just picking from a list, it's about matching the right solution to the right problem.
Okay, last section. Section 5, Frameworks for Implementation. It's so important to remember that none of this engineering work happens in a bubble. For any of this to work at scale, you absolutely need a strong ecosystem of policies, standards, and support.
And this is what that ecosystem looks like. You've got legislation setting the rules of the road, things like the Energy Policy Act. You've got federal programs like FEMP that help prove out new technologies. You have international standards, think ISO 50001, to give us a common playbook for energy management. And of course, you have critical R&D support from places like the DOE. It's all these layers working together that makes progress possible.
And really, it all boils down to this quote: "A diversified portfolio of energy technologies is crucial for addressing emissions mitigation cost-effectively and for political reliability." That's the whole game right there. It's not about picking winners. It's about building a smart, resilient, and reliable portfolio.
So I'll leave you with a final thought to chew on. As all these systems get smarter and smarter, are we reaching a point where the main job of a renewable asset isn't just generating energy? Could its real value actually shift to providing grid stability and other services? It's a big question, and it's definitely something to think about as we all continue to build out the future of our energy systems.